We're rolling. So, this is our second example of the last lesson in Unit D curve sketching, the lesson that my esteemed colleague called Putting It All Together, which is pretty appropriate. It kind of rolls all your calculus skills and your curve sketching skills into kind of one activity. And we've done the actual calculus part here for you. Right? We've got the original equation is x to the power 4 minus 8x cubed. Here it is in factored form. Here it is as a first derivative, and then in factored form. And here it is as a second derivative, and then again in factored form. So the derivatives have been done for you. But this one's actually, I think, quite a bit easier than the rational one we did yesterday. And you know that this thing, you know some things about it just kind of looking at it, right? It's a polynomial with an x to the power 4 as its highest power, which means, and a leading coefficient that's positive, which means that it has both arms going in the same direction. So I'm expecting it to go up forever in both the left and right sides. And my analysis here will probably bear that out as we get going on it. So first, let's do the intervals of increasing and decreasing. So let's see. Is my pen on? Yeah, my pen's on. Okay. So we set the first derivative to 0, and much easier to do this in factored form. And what do we see? Well, we see then that means that x is 0 and x is 6. Remember, you also look, when it comes to looking for critical values, make sure that you're also looking at any place that x doesn't exist. Well, this is a domain. In fact, the way the textbook organizes doing this, instead of kind of the order we have on this chart, you'll see that the textbook actually asks you to think about domain first. So right away, you're looking for those. I think the reasoning for that is that it right away reminds you that, oh yeah, if I'm thinking about domain, I think about the possible places that could be critical values, or because it's where the function doesn't exist. So the first derivative exists everywhere, right? This is just a cubic. So there are no other potential critical values. But when I have 2 points, I like to break out the interval notation. So they're the interval chart, I should say. So what happens when we're smaller than 0? We're between the two values, and we're bigger than the biggest value. Okay. I mean, you could avoid this chart and use greater than, less than equations if you wanted to, but I don't know. I find the chart easy to kind of organize my thinking. So I have two factors here. I have x squared. The 4 obviously doesn't really matter. And I have x minus 6. And all I care about is, on these intervals, is the derivative positive or negative, which tells me whether the function's going up or down. So this one's always positive, so I might as well just fill that in. But x minus 6 is negative when I'm smaller than 0, negative when I'm between 0 and 6, and positive when I'm bigger than 6. So a negative and a positive make a negative, so that means we're decreasing. Positive and a negative is also negative, which again means we're decreasing. And a positive times a positive is positive, which means that we're increasing. So basically, there's no change at the 0 point. So 0 is not really a critical value. It could be a point of inflection. We'll figure that out later. But it's definitely not a local max or min. So we're decreasing from negative infinity all the way up to 6. And we're increasing from 6 to infinity. Okay, and that kind of, again, leads us to exploring local max and min. If there's no change in direction at 0, then that's not a max or a min. But if I go from a decreasing to an increasing, right, at x equals 6, I go from a decreasing to an increasing. So I have a local minimum, and I'll run 6 through the original formula. And I've already done the button punching on that. And I get negative 432. So there we go. We've dealt with local maxes and mins. We don't have any local maxes, but we do have a local min. at 6, negative 432. And we actually also know that it's an absolute min, because we know that the two arms, again, we talked about this, the two arms have to go up forever. All right, let's deal with concavity. So for the concave test, we go to the second derivative. And let's use the factored form again. Set it to 0 and find that the 2 points that matter are when x is 0 and x is 4. Again, there's no points to worry about where the function doesn't exist. This thing exists across all reals. So again, 2 points means that I kind of prefer doing it as a chart. So it happens when we're smaller than 0, we're between 0 and 4, and we're more than 4. So what's this thing doing? Does its concavity change? In which case we would have inflection points. Well, 12x, again, don't worry about the 12, but x is going to be negative, then positive, then positive. The other factor, x minus 4, is going to be negative, then positive. So the derivative is positive for the first interval, negative for the second, and positive for the third. So yep, we have concavity changes. That means that when we're positive, we're concave up, right, which means it does that. And then this one is negative, so it's concave down, which means that. And then it's concave up again, which again means that. So I'll make a kind of conclusion. Therefore, I guess I should put a therefore on those. Therefore, we are concave up from negative infinity to 0, and then again from 4 to infinity. And we're concave down from 0 to 4. All right, so that means, I should maybe go back here, since concavity changes at 0 and at 4, we have 2 points of inflection where this thing is going to change its direction of concavity. And 0, going back to the original function, is just the point 0, 0. And plugging the 4 into the original function, you get negative 256. So this thing's going to be an easier graph to think about than yesterday's, because yesterday's was irrational and it had, you know, more things to deal with. But this one's going to be kind of a pain to graph, because we're going to have to really think about what our scale is. Asymptotes, we don't have any, and you can of course prove that really quickly. There's no non-permissible values for vertical asymptotes, right? And for the horizontal asymptotes, you always just take the limit as x approaches infinity. And for something that doesn't have any denominators, it's just going to infinity. And the limit as x goes to negative infinity is also just going to positive infinity. So again, both arms are going up. So therefore, no horizontal asymptotes. And vertical asymptotes, there's no non-permissible values. Therefore, no vertical asymptotes either. So that's pretty easy. X-intercepts, the original function is, again, if I set y to 0, I get x cubed and x minus 8. So that means 0, 0 is a point, and 8, 0 is a point. So it has two x-intercepts, and the y-intercept, well, we got it already. It's 0, 0. So I think I'm ready to graph. I know what direction it's going. I know where a bunch of points are that I can put on it. Okay, skip past this diagram and go to this one. Now, because the scale on this one kind of gets kind of crazy, we have to count in much larger numbers on the y-axis than the x-axis. So what do we know? We know we have x-intercepts at 0, 0 and 8, 0. If there were asymptotes, I'd be drawing those first. Then we know that both arms go up forever. So after 0, it's just going up forever. At 0, it's changing directions, and it goes to concave down until it gets to 4. And what was it, 4? Negative 256. On this scale, that's going to look pretty much like the middle between 200 and 300. So it changes from concave down to concave up here, and then it dips down to make it as far down as, what was it again? 6 and negative 432, which would be, I don't know, about a third of the way. Okay, so it goes concave up here. Oh boy, I don't like that already. Concave up here. And then it changes to, or I should have said concave down. Then it changes to concave up. And at this point, it's back to being concave down. And then it swings back up that way. So I think that's my graph, I think. Yeah. All right, as always, the most fun part is checking to see how this looks on Desmos. See how close my analysis got me to the real deal. And I think I forgot to open Desmos this morning, so give me a sec. And let's see, are we logged in? Sometimes it doesn't log me in automatically. Yeah, I'm logged in. Okay, so let's see. Where are we? No, that's for my other class. There it is, 5.5 example 2. Oh, that looks pretty good, doesn't it? That's pretty close. I'll take that. I maybe made this a little too pointy. But otherwise, I'm quite happy with that. That's roughly the same scale that the picture is. Okay, so there we go. That's 2 examples. The first example was a rational. This example was just a polynomial. And now, when you go to the homework is 5.5. And we're going to give you just a couple of classes here to play around with these. We kind of hope that you're actually not doing, I was calling it homework, but I'm actually kind of hoping that we're giving you enough class time that you can just play with these in class. You don't have another test staring you down the face. We're not doing any more assessments. So you can, kind of focus your evenings on whatever courses you have to finish essays, and perhaps I know a couple of you might be studying for final exam or final assessments in physics or chem or whatever. So basically, you just get to come in for the next couple of days and play with curves. I always find this really fun. I love the challenge of seeing if I can make this picture as reasonably accurate as I can compared to what Desmos shows me it's going to be. Now, the book does kind of ask for a specific order of things. I don't really care if you follow this order or not. They have it very kind of laid out. A, figure out the domain. B, your intercepts. C, your symmetry. Oh, you know what? I forgot to talk about symmetry because my colleague didn't put symmetry on the sheet. Let's go back really quick here. Right at the bottom of the sheet, I would maybe talk symmetry. We weren't sure if we were going to get to the symmetry lesson or not, so we didn't bother putting it on here. But okay, let's take a quick peek about symmetry. Remember, symmetry comes from understanding if this thing is odd or even. So is it odd or even? And the answer is it's neither. And how do I know it's neither? By looking at the formula. Here, I'll just do it over here. Well, the equation. Well, the equation was y equals x to the 4 minus 8x cubed. So call that f of x, first of all. And then, if you run negative x through the equation, and you get the exact opposite of the equation you're looking at, then it's odd. If you get the exact same equation that you started with, it's even. Notice this one's neither, because if you plug in a negative, it gets canceled on this one, but it doesn't get canceled on that one. So this is going to be x to the power of 4 plus 8x cubed. That is not the opposite. Some of you who remember your grade 11 terminology might know it's called the conjugate, right? But it's certainly not the opposite. So this has neither, and my picture backs that up, right? Because notice there is no symmetry right here. If you rotated this arm 180 degrees this way, it doesn't match this arm. So nope. So there we go. All right, back to the textbook again. So, or the workbook, I should say. So the workbook here does it in the order of domain first, then intercepts, then check to see if it's odd or even. Then look for asymptotes. Then the part that we started with. Do your intervals of increase or decrease using critical values. Then use that to decide if you have local maximums or local minimums. Then use your second derivative And remember, there is a second derivative test for local max and mins. I kind of didn't bother using it in the two examples today, but if you'd like to, you can, you have more than one tool in your toolbox. You can use the other second derivative test for max and mins too. Then there is the concavity, points of inflection, and then finally H is give me a sketch. So if you like kind of the order they do it, you can follow that, or if you like kind of the template that Mr. L kind of put together for us, you can use that. And when it comes to sketching the curve, just break out a piece of graph paper and see how close you can get. So there's 12 of them on here. Some of these take a few minutes, but again, I don't necessarily think you have to rush home tonight and do it all as homework. You're going to have time to work in class tomorrow and Thursday on this, and I'm here to help you if you get stuck. Okay, so kind of a nice, fun end to the course. We're just gonna graph curves. I'll stop the lesson there. That's all I wanted to get through today.